Hello, we are from Group 8. We will present to you the pipe network analysis project in fluid mechanics. First of all, we'd like to thank you, our lecturer, Wan Nur Aliza binti Ahmad, for supervising us throughout this project. Let me introduce the members of Group 8, including myself, Valentine, Jovita, Shavinesh, and Christina. So, our project is about pipe network analysis. As we know, the analysis of piping network is a calculation of fluid flows and pressure drops in complex piping system. Pipe networks are important for public utilities supplying water to consumers, natural gas distribution planning, or any system that involves piping. Pipe network involve pipes of different diameters that are connected by various fittings or elbows to enable the flows of fluid within the network of pipes. Throughout the flow of pipes, we know that there are major losses that are associated with frictional energy loss. Hence, in this project, we can determine the energy loss in pipe flow by using the Darcy-Weisbach equation. That is all from me. Thank you.
Hello everyone, my name is Christina, matrix number A of 210122, and I will be briefly going through the methodology of this project. A little short introduction for the Hardy-Cross method, the method I'll be using for this project. Cross is an American structural engineer and developer of the moment distribution method that was named after him. The method is an application of continuity of flow and potential to iteratively or repeating a set of steps to solve fluid flows in a pipe network. Or a better definition taken from Madame Ariza's lecture notes, the method involves a series of successive approximation and corrections of flows in individual pipes. Alright, now let's move on to the method itself. Since the data set of friction factor, diameter, length of pipe, inlet and outlet discharge is given, the Darcy-Weisbach equation is used to calculate the head loss, which is given HF equals to 8FL2 squared divided by pi squared G d to the power 5. Then the K of each pipe is calculated, which is given by K equals to 8FL divided by pi squared G d to the power 5 with n equals 2. And by combining both equations, you get HF equals to KQN to the power of n. Next, by referring to the figure provided, as you can see to the right, direction of flow distribution is assumed and further divided into 4 closed loops. Now, a few assumptions should be taken into consideration. First, total flow of in should be equal to the total flow out at every joint. Clockwise flow is considered to be positive and vice versa. Lastly, the flow must satisfy the pipe flow friction laws in a single pipe. For this, from the schematic diagram of pipe network, as you can see, the direction of flow is assumed for loop 3, 4, 5, and 6. Alright. For the first trial, Q1 of other pipe and correction are calculated. The HF for each pipe is calculated and the sign of flow direction is to be retained. Consequently, HF for each pipe is then calculated using the formula HF over Q equals to K Q to the power of n minus 1. However, the sign of the flow direction is disregarded for this part, and the results are then tabulated as such manner. Afterwards, the correction delta Q is to be determined using the formula delta Q equals to total HF divided by delta Q is to negative total HF divided by total N times HF over Q with N equals to 2. And apply it to the correction algebraically to the discharge of each member of the loop. Subsequently, for the adjusted Q, or in this case the second trial, Q2, is then calculated by correcting the assumed pipe P11, P7 plus 4, P13, and P9. The previous steps used to calculate the first trial are to be repeated until the delta Q of Q2 becomes a figure as small as 0.000 other numbers for at least 2 loops.
My name is Jovita Tan and my matrix number is AF210088. I will talk about the result and calculation for our project. This is the data given by the question, which this is the schematic diagram of pipe network. The frictional factor, inner and outlet discharge, and the equation of head loss is also given. Firstly, we find the value of K by using Microsoft Excel. Key in the data given by the question. The diameter of the pipe is given in the unit of inch, therefore we need to change it to meter by multiply 0.0254. Then using the Dancy-Weisbach equation to calculate the value of K. So this is the table show the value of K of each pipe. Next, this is the schematic diagram of pipe network, and we fill in the outlet and inlet discharge. Then assume the direction flow distribution, fill in the K values, and now we can start our first trial. Assume discharge Q1 of pipe 11, pipe 7 plus 4, pipe 13 and pipe 9, and calculate the Q1 of other pipe by using the equation of pipe in series and pipe in parallel. The assumed value is referred to the value of K of each pipe. When K is larger, Q will be smaller. Therefore, the value of Q for pipe 11 must larger than pipe 12. So this is the calculation of our result. We are using Microsoft Excel to calculate this pipe. First, key in the data of K of each pipe. Then we key in the formula of the relation of each pipe. For example, pipe 12 is inlet discharge 0.09 meter cube per second minus the value of Q1 of pipe 11. Then we fill in the value of the assumed pipe. Each loop will have one assumed pipe. Next, we calculate the value of HF, which HF is equals to KQ power n and n is equals to 2. And we consider the clockwise flow to be positive and the counterclockwise flow to be negative. And then we calculate the NKQ power n minus 1. Last, calculate the correction delta Q by negative sum of HF divided by sum of NKQ power negative n minus 1. So this is the calculation for trial 1. Now we go to trial 2. Q2 is calculated by correcting the assumed pipe. In trial 2, we copy-paste the calculation in trial 1 and delete the value of the assumed pipe. The Q2 of the assumed pipe is calculated by sum up Q1 and the correction delta Q from each loop. So this is the result for trial 2, and 2 loops reaches 0.00xx value, which is the loop 4 and loop 6. Therefore, we can stop the calculation at trial 2. This is the result of the value of Q for each pipe. And this is all from me. Thank you.
Good morning to the Honorable Lecturer and my fellow teammates. Right now I'm going to present about the ending of our project, of our fluid mechanics project, which is the conclusion. So let's take a look at it. Okay, the network of pipeline which connects to the consumers or users are called as distribution system. They are very important because they play a pivotal role in the lives of us. For an example, domestic, commercial, industrial, and also firefighting purposes. These are just few examples, but you can understand on the importance of distribution system of the network pipelines. So, a little backstory about this conclusion is we will know how important the distribution system is, what type of formula we use to tackle the problems in our project, and many more. So, regardless of the differences in pipe network, everything has the algebraic sum of pressure that drops around a closed loop must be zero. There can be no discontinuity in pressure, as well as the flow that enters the junction, which is the starting point, must be equally same with the flow that leaves the ending point. So the starting point and the ending point should be similar, exactly the same. Analysis of discharge Q is needed in every pipe for this water supply system in town A by using Hardy-Cross method with Darcy-Weisbach method as listed in the results. So this is the methods that we use to calculate our results. Thus, for our project data set of friction factor, diameter, length of the pipe, and the inlet and outlet discharge is given. The head loss is calculated using Darcy-Weisbach equation. Therefore, the K of each pipe is calculated. So the K of each pipe is not ignored or pushed aside, but it is actually taken into consideration. So in a summary, a good distribution system should provide proper water pressure at every consumer lives. The pressures should not only be great enough to properly meet emergency situations as firefighting needs, but should also not be excessive due to the pressure leakages, which is cost effective. However, a booster pump is used to provide to higher floors in tall buildings or skyscrapers. Moreover, distribution system of purified water should be completely watertight, and the purity of distributed water should be checked regularly and maintained. Most importantly, the maintenance of the system should be economically stable and easy to handle. And that's all from me. Thank you.